Es lo que necesitas para... Sí, referencia. Recetas es el mismo que se va a hacer en Intercycle, el ranking. Así. George Cáceres.
Un servicio social.
Súper bien.
Si alguien ha visto el libro de memorias del ingeniero Carlos Ruiz, está marcado en la primera página. Está también el número de teléfono, le agradecemos por favor entregarlo o en la continuación, donde está la señorita Daniela Vázquez, o acá en el evento. Gracias.
Buenos dias. I'm going to start talking about liquefaction by talking about the state concept and how it provides a useful framework for understanding sand response under monotonic shear, and then that will be extended into cyclic loading by Professor Kramer. Much of this work is based on the textbook by Professor Kenji Ishihara, 1996, Soil Behavior and Earthquake Geotechnics. I think required reading in geotechnical earthquake engineering in their area of liquefaction is at a minimum the book by Professor Kramer, the book by Professor Ishihara, the Jeffries and Bean second edition of the critical state book that was published in 2016, and also the Seed 1979 journal paper that you have in your references. Those, and Idris and Boulanger in 2008. Those are the 5. You have to read those 5 books and papers multiple times before you read anything else in this field, because they really provide so much depth and fundamentals. You never forget your first kiss or your first sand boil. This is my first sand boil. Professor Ross Boulanger and I were a team that went out to the Bay Bridge area and witnessed the liquefaction of the sand boil. This is Professor Boulanger's hat. He's not standing there. He's not that short. He took his hat off for scale. This is 30 centimeters. This is an amazing amount of ejecta and damage. And we often use sand boils or ejecta as an indication that liquefaction has occurred. More important than the triggering of liquefaction is the effects of liquefaction. Things that are light can lift out of the ground. Things that are heavy can sink into the ground and tilt. Lateral spreading can damage bridges. Probably one of the worst consequences of liquefaction is the ground deformation can break gas lines and also break water lines. At Balboa Park in the Northridge earthquake, the liquefaction-induced movement broke a gas line, which unfortunately led to a fire, which killed, I think, 4 people. And there was areas where they were not able to put fires out because they had lost the water pressure because of breaks in the water line. When I first went to the San Francisco Bay Area in the late 1980s, and I talked with elderly people that were alive as teenagers during the 1906 earthquake, they always said, "Oh, you mean the 1906 San Francisco fire?" It's the fire that devastated the city. The earthquake may have been the match that started the fire, but it was the fire that consumed and killed so many of the people. The 1923 Kanto earthquake in Japan killed 140,000 people, primarily because of fire. The Kobe earthquake had devastating fire as well, and almost 6,000 people died, but the damage to the ports were also important. They had 186 berths to offload containers. All but 8 of them were put out of service because of liquefaction. Only one geotechnical engineer knew about liquefaction and thought you could have it in this city away from the major subduction zone, and they had done ground remediation. Those 8 berths were in operation. Osaka Harbor is still recovering financially from this earthquake that occurred almost 25 years ago. We talked yesterday about volume change. If you can ask, I talk to soil. Sometimes soil talks to me. But when I talk to soil and can ask it a question, the number one question I would ask soil is, what is your volume change tendencies during drain shear? Because if I know that, then I know a lot about the soil. So as we talked about yesterday, we have soils at high void ratios, low relative densities, that under typical confining pressures are contracted. The void ratio reduces during drain shear. We have dilative soils that contract a bit, but then they dilate in drain shear to get to the critical void ratio. And importantly, that critical void ratio and that response is stress dependent. So soil response is state dependent, the void ratio relative density that you're at, but it's also stress dependent. The critical state line is the place where soil has to go. If it's above it in constant confining pressure, it goes down on a vertical line, and hence it's reducing void ratio is contracted. The dilative soil contracts and then dilates to the critical state line. We can't just talk in terms of relative density or void ratio, because we can have a soil that has the same relative density, and at low confining pressures it's dilative, at high confining pressures it's contractive. We talked about loose and dead sands during volumetric that allowed to undergo volumetric strain because they're drain tests. And we saw that although they initially contract, that there is a difference, that the dilative soil is dilating. It's actually expanding against an applied stress field. That's work, and so that's why it takes more stress to fail those soils, and that's why peak friction angle is a function of the tendency of the soil to dilate in drain shear. The loose sand is always contractive under this confining pressure, and so it's always in the contractive regime. It contracts rapidly, and then the rate of contraction reduces, and you eventually get to steady state. Everything we know about drain behavior can be translated over into excess pore pressure generation for a saturated soil during undrained shear. So understanding the volumetric strain response is so critical to the undrained response. We should always say, when we're talking about undrained tests, volume strain tendencies. And we'll say this soil has a contractive tendency. This soil has a dilative tendency. We will shorten that and say the soil is contractive and shear and dilative. Obviously, you cannot change in volume during an undrained test of a saturated specimen. And so realize the terminology is the soil would like to contract, but instead of being able to contract, it's generating excess pore pressures. So see the connection between the volume change tendencies in drain shear and excess pore pressure, which if the excess pore pressure is increasing, that means the effective stress is decreasing. So this connection between drain shear is so important to understanding undrained shear and changes in effective stress, which change stiffness and strength. Remember, one of the most important principles is the effective stress principle. If we have a vertically propagating horizontal shear wave, the total vertical stress during that earthquake event is not changing. So this is zero. And so if we have a buildup of positive pore pressure, then we're getting a change and a reduction in the effective stress, and that's the key issue. So soils that are dilative are getting stronger and stiffening because of these temporary effective stresses that are because the soil would like to dilate, but it cannot. So it's expressed by a negative excess pore pressure, and therefore the effective stress is increasing. But it's the cases where things are contractive or highly contractive in drain shear that lead to large pore pressure generation and significant reductions in effective stress. A very important parameter developed by Bean and Jeffries in '85 is the concept of the state parameter. If this steady state line is so important, and we know that states and stresses above it have contracted behavior, and soils below it have dilated behavior, it would be useful to know how far we are away from the soil, from the steady state line. If we're here, we are contractive, but it only has a little bit of contraction, or in undrained shear, a little bit of pore pressure generation to get to the steady state line. If we're here, then the soil is more contractive in drain shear. It generates more excess pore pressure. There's a greater reduction in effective stress to get to the steady state line. Up here would be even worse. So using the void ratio that you're at minus the void ratio at the same effective stress on the steady state line as a reference parameter is incredibly valuable. The state parameter and the state concepts I'm talking about are so important that I would argue that you should not do effective stress analysis of a saturated sand without using a model that has this critical state framework and the state parameter as an underpinning to it. No matter how sophisticated the model is, if it doesn't build on this state concept, you are missing one of the most important things about soil response. As I mentioned yesterday, it's not as simple as we'd like it to be, and the soil, because of fabric, goes to a quasi-steady state line before it gets to that final destination of a steady state line. And so we just recognize that so for example, in terms of Q, deviator stress, versus P prime, the mean effective stress, the soil is not going to go directly to the steady state line, but it actually, you can see it, if it's moving to the left, that means the effective stress is reducing. If the effective stress is reducing, the reason why is because you're basically getting pore pressure increase. You get to your peak strength, and then there's this collapse mechanism, this unstable, this rapid generation of pore pressure. Things go from getting bad to getting very bad quickly. It dives down to the quasi-steady state line. That's where you get to a strength that is probably important for engineering consequences. If it was to stay together, it would dilate and it eventually eventually has to get, and it will get, to the steady state line. A soil at a lower confining pressure at the same relative density will not have to contract as much, so it won't generate as much pore pressure to get to the quasi-steady state line and then move up. But you can see for this soil, it is actually got a relatively low peak strength, and then its residual strength at quasi-steady state is actually relatively low. And it may never get to the full higher level in practice in the field. So if we look at soils that would like to dilate, we see two bends in the stress strain curve. This is deviator stress or shear stress versus shear strain. Soil response is elastoplastic. So as you're loading this dense soil at a relatively low confining pressure so that it would want to dilate and drain shear and undrain shear, you get this first yielding, but then as the soil crosses the phase transformation line, it then starts to dilate or wants to dilate, so we get the buildup of negative excess pore pressure and we get a stiffening effect because of that dilation. So that's the dilative sand. Of more concern, in many cases, is the contractive soil response, because the soil actually starts to build up its strength. Water pressures are increasing, but as the water pressure goes from 10 to 20 to 30% of what was the vertical effective stress, things are stable. Once you get beyond about 40, more like 50 to 70% pore pressure generation, where the excess pore pressure is, let's say, 60 to 70% of what was the vertical effective stress, things become unstable, and there is an instability that causes this to collapse. And this high rate of pore pressure just builds on it. Because it's collapsing, the excess pore pressure goes up even faster, and because it's soft, it strains more, and then the excess pore pressure increases faster, and you get to a flow regime. And you can, with very loose soils under sufficient effective stress, you can get to a nearly flat steady state line, a flat stress strain curve. These are the two extremes. There is the case of limited flow, where things come up to a peak, they come down to a quasi-steady state, and then they dilate, or they want to dilate, and so we have a stiffening response. This is a very good diagram to study because we have shear stress versus mean effective stress, or the QP prime plot on the left side, and then we have the stress strain curve, shear stress versus shear strain on the right plot, and we're looking at those three cases. The case where the soil, you can see that yes, you're building up some pore pressure, but notice how it's always increasing in shear stress. There's never a case where the shear stress goes down, and then it hits the phase transformation line and it basically dilates. And you see that in terms of shear stress versus shear strain. It comes up, it's always increasing. It's a cyclic mobility, or in this case, monatomic loading, so it's a stable response. That's different than this case, where there's a more rapid increase in pore pressure because the effective stress is reducing. And then we have this flow or instability with rapid increases of pore pressure, where this dives down to a nearly zero value. And so we have a buildup of stress, but then at a certain strain, and it's not large, it collapses down to a low residual strain. And then we have the limited case between the two, where we have limited flow. It has a peak. There is a moment where the shear stress is actually reducing because of the increase in pore pressure and the softening, but then we hit the phase transformation line, and then it dilates. And so you see a peak strength, then it drops down to a quasi-steady state strength, and then it dilates or wants to dilate, and therefore increases effective stress to get to the final point. Density is one of the most important things to capture. These are some tests run by Professor Chibanowski when he was working in Japan with Professor Ishihara. 6 undrained torsional tests. Torsional tests are probably the best tests you can perform because of the less problems with boundary conditions and more uniform strain across the specimen. He's running these tests under the same isotropic mean effective stress. So P prime is 100 kPa. Actually, sigma 1, sigma 2, sigma prime 3 are all 100 kPa. Then we have different relative densities. So we're only looking at the effects of low relative densities, very loose to loose soils, to medium dense soils, to a dense soil when we get to 80%. And again, there's 2 plots. We'll eventually show you 4 plots, but these are the 2 most to look at in terms of consequences. You can see how the very loose soil contracts and gets down to nearly 0 strength, and you can see that in terms of the stress strain curve. You can see the dilative soil that is strain hardening, and you see that response there. Then you see in between cases, and the yellow case is the case for a relative density of 40%, where it comes up to a peak, there's a little bit of a flow regime, and then it dilates. The point where it goes from contractive tendency to dilative tendencies is the phase transformation line. And so you can see the consequence is it comes up to a strength, it drops to a quasi-steady state strength, large strains occur, and then after those large strains occur, it does have a tendency in undrained shear to want to dilate, which is expressed by stiffening because the effective stress is increasing. If we look at the effects of confining pressure, we looked at relative density, but now I'm going to take one test series where the relative density for all these tests is 38%, but the soil is consolidated isotropically to different mean effective stresses. 0.1 megapascals or 100 kPa, all the way to higher confining pressures of 3 megapascals, which might be the sand beneath the dam that you've been placed and now is being drained or being loaded in undrained shear. You can see that at low confining pressures, this soil that's loose, 40% relative density, contracts a little bit, but it primarily dilates to get to the steady state point. Whereas this soil, which is the same state, the same relative density, is highly contracted. It moves far to the left and builds up high excess pore pressures, gets down to a low mean effective stress, and then dilates slightly. So you see this type of response for the soil that would like to dilate. You see this kind of, for the soil that wants to dilate, which the soil that wants the highly contractive soil is coming up, hitting a peak, and then dropping down. Whereas the soil that's highly dilative, because it's constantly building up negative excess pore pressure or increasing effective stress, is getting this stable type of response. If we do the same experiment of looking at the effect of confining pressure, but now look at a higher relative density, 64%, you can see the same kinds of things, but because the density is higher, it is more dilative relative to what we saw in the previous slide. This will dilate even more because it is a denser soil, and the soil at the high confining pressure will contract, but it doesn't contract as much. It doesn't move as far to the left in terms of its effective stress. It doesn't build up as much positive excess pore pressure, and then it hits the phase transformation line and then dilates. And so you get a response that looks like this. So it's amazing that soil response is as complex as it is, yet this critical state framework, by just looking at the interplay of relative density and effective confining pressure, drain shear and undrained shear can connect everything together and essentially tell us so much about soil. We believe, and I think it's a useful framework, to say that we eventually get to steady state. That soil will get to steady state. And so it's important to buy into that. Now, we can have some debate on how much strain it takes to get to steady state. We can have some debate on is triaxial extension and triaxial compression and simple shear, do stress path matter? You could say that when you see differences in those tests, it may be because of the boundary constraints of those tests. It is not a major, it's not a limiting assumption, it's a useful assumption, it's a realistic assumption to assume that soil will go to steady state, and there's a unique steady state line. So we want to develop that steady state line. So let's go back and look at the test series I looked at that had a relative density of 38%, but run at different confining pressures. You can look at things in the QP prime plot and the deviator stress axial strain plot, but it's always nice to think about critical state lines, steady state lines, and look at void ratio versus P prime. So in this test, we know that we're starting at a high confining pressure. It is an undrained loading of a saturated material, so it's constant volume. This is at a low effective stress. We know where it wants to go. It has to go to the steady state line. It has to go to that steady state point. And the soil to the left in blue has to move over to the right to get to that steady state point. And so this is a useful framework for tying all these tests together, even though they're run over a large range of effective stresses. If we go to the other test series that I showed, where it's a relative density of 64%, void ratio versus P prime, that's the previous test series. But now we're looking at a soil that has a void ratio of 0.735. We have our initial states shown in high and low effective confining pressures. We know that it will not contract as much. It actually contracts and then dilates and gets to the steady state point. We know where the steady state point is. And then we know for the lower void ratio material, it has to actually have a large increase in effective stress. It has a large dilatancy tendency to get to the steady state line. If we can do this test at two void ratios at a range of stresses, we can do it at 5. We can do it at enough to where we can construct a unique steady state line for each soil. There's tremendous value to investing the effort into doing monotonic, undrained shear tests to capture this steady state line. The shape of the steady state line has changed. It's still void ratio, but now we're plotting the log of P prime. We're plotting this on a log plot, so we can go over a wider strain range, or stress range. And these are, I think, 70 undrained triaxial compression tests. They were done by other investigators, including Professor Chupanowski, but he compiled them as part of his thesis in developing a framework for his stress density model. And you can see that all these tests done by different investigators on the same sand, it's the Toyo sand in Japan, all form a relatively unique relationship in terms of the steady state line. The open boxes are all the initial states of void ratio and effective stresses the test started at. So for example, if we know the initial state is an undrained test, we know where it's going. We know it's going to steady state. And so this ability to take drain response and undrained response and tying it all together is an incredibly useful framework. I have found the only way to really get this internalized, you don't want this to be an enemy. Critical state soil mechanics is not your enemy, it's your friend. It's a framework to help you interpret things. It is not perfect, it's idealized, but it allows you to get in the game. The way to do this is find a book by Ishihara or Bean, Jeffers and Beans. This is discussed in Kramer's textbook as well. This is discussed in Idris and Boulanger 2008. Find one of those books, study it, and then take a blank piece of paper and draw all of these things. Say, okay, I have a very dense sand under low confined pressure. I have a very dense sand under high confined pressure. I have a very loose soil with a very high void ratio and low relative density under high and low effective stresses. And then I have cases in between. If you can draw all these plots I'm showing you on a blank piece of paper, then you have a friend in the critical state framework to help you interpret real soil. It's so important to be able to have this, to say, this is what happens in a drain test, this is what happens in an undrained test. This is what happens to a soil on the dilative side in terms of drained and undrained loading. So if the soil is sheared monotonically, the state concept says there's a steady state line, and above it is contractive world, and below it is dilative world. And you know everything about the soil. You know some of the most important things about the soil when you have placed the soil in one of these states and confining pressures. It's the state, the void ratio, or relative density, and it is the effective stress combination that allows you to place a soil in one of these areas. Now, one of the ideas that is the basis for the stress density model that Professor Chubanowski and Professor Ishihara developed is to use the steady state line as a reference and realize that if I am far above the steady state line, if I have a high state parameter, then I'm at a point where if I can move to the left, especially this is where the void ratio E naught is where I have an effective stress of P naught. So if I'm up in this area, then I'm going to definitely be a flow. If I'm maybe here, I will still get a flow phenomenon. The soil is moving rapidly to the left, which causes a buildup of shear stress that then collapses down to the residual strength, and I get a flow failure. If I'm below this initial dividing line, it would initially want to contract, so I have a reduction in mean effective stress, but then it has to dilate to get to the steady state line. I know I'm getting this stable response in monotonic loading of monotonic undrained loading. And then I have a limited flow case where I go off to the quasi-steady state line and then come back, and so I get this intermediate behavior. The state parameter is one of the most important concepts, and that's why I think you have to use a model that includes the state parameter, because it tells us, for example, if we have a positive number, then we are above the steady state line. If we have a negative number, we're below the steady state line. How big that positive number is how highly contracted it might be, and how negative that number is tells us how dilated it is. And so that kind of index is incredibly useful. What Professor Ishihara and Professor Chubanowski, much of it built on the work that Ramon Verdugo did experimentally at the University of Tokyo, was to go one step further and say, let's develop something called a state index. It's defined here, let's don't just take the value of where I'm at minus the point on the quasi-steady state line or steady state line, but let's use it as a reference. Let's look and say the biggest difference I could have is in blue, is from this upper reference line down to where I'm at, and I'll normalize that vertical distance by the separation between the upper reference line and the steady state line or quasi-steady state line. This upper reference line is if I took a very loose sand at a high void ratio and did isotropic consolidation, but it's capped by a horizontal line that is at the value of E naught, where E naught is the value of the void ratio at a mean effective stress of 0. I took this from a paper and I just realized that they have P here. That's a typo. This should be P prime. It's always going to be the mean effective stress. So if I have states above the upper reference line, it is going to run, not walk, run to the left and undrained shear, and I'll get a flow failure. If I am up in this area, I probably will get limited flow, and if I am below this, I will get a little contraction and then head off at constant volume to the steady state line. Realize if IS is 0, I'm on the upper reference line. If IS is 1, I'm on the steady state or quasi-steady state line. If IS is greater than 1, I'm below that. The power of this, let's go back and look at 3 tests. They all have the same state parameter, or they all have the same state index. They're at different void ratios. They're at different effective stresses. But the thing that they have in common is there's the same distance from home. They are eventually going to go home. And they're about the same distance from home. And because of that, by being about the same distance from the steady state line, you can see that the first test builds up and then undergoes some flow. The second test builds up some stress and then undergoes flow. And the third test builds up some stress, undergoes flow. Because they are the same distance away from the steady state line, they have the same state parameter, the same state index, they have similar shapes. So if you're somebody who likes to mathematically model soil, you should not be able to contain your excitement right now. You have seen the light. You say, if I can develop a model and I have this state index or this state parameter, I can take all these different behaviors at all these different confining pressures and void ratios, and in terms of stress-strain response and undrained shear, they are all similar in shape. I just have to be able to differentiate between the peak. But boy, I have a lot of power in this concept. Now, there's some questions about the critical state line, but I think this is one piece of evidence. There's a lot of other evidence that say it's reasonable. Let's look at the drained angle of shearing resistance. This is the peak friction angle versus the state parameter. It's amazing that you can take all these tests done on very different sands. Now we're looking at all these different sands. We're not just looking at the Toyota sand. Done by different investigators, different PhD students, different labs. And we see something that gives a unifying factor to explaining all of these test results in terms of its drained friction angle is the state parameter. The more negative the state parameter, the higher the peak friction angle. If we get to 0, we're essentially getting to the residual strength. These tests are actually probably not quite getting there, and that's why they're lower friction angles. So when we look at this upper reference line and the quasi-steady state line, and then other values of the state index going above 1, so you're below the quasi-steady state line. With these tests, at different confining pressures and different effective stress, we see a commonality in the sense that as the state index increases, we're progressively getting a stronger, stiffer response, but the shape of the curves are very similar. If we look at ranges, so we have tests now that have a state index between 2 and 3. We have a series of tests that have a state index between 4 and 5.6. And you can see that the higher state index soils lie above the lower state index soils in terms of stress-strain response. You see that also here. So I think I've hopefully driven to the point that with similar values of the state index, which is a little bit better than state parameter, but you could pick one or the other. I'm happy with state parameter as well as state index. By having similar values of the state parameter or state index, you get similar shapes of the stress-strain curve, hence similar stiffnesses, similar strengths. The stiffness and strength increases as the state parameter value increases, or they increase as the state parameter becomes more and more negative. Knowing this quasi-steady state line and the initial state of the sand, you can calculate this value of the index, state index, or the state parameter. If you know that, you can predict the stress-strain curve. So these are key parameters in soil response. Realize that if you are between Emax and Emin, but you can be above Emax, you can be below Emin, but if I'm in these locations where I'm above the upper reference line, I am in the flow regime. If I'm in this area, I might get some flow and then might basically come back to the steady state line. If I'm here, I've definitely got no flow. And so this is telling us that even though we call it liquefaction, there's not liquefaction. There really is cyclic mobility with unlimited strain potential where you can have flow liquefaction. And then there's cyclic mobility with limited strain potential where you may accumulate deformation, but it's a relatively stable response. And then you have something in between. Very interesting study was done before the earthquakes at Christchurch. So we really focused on this and trying to understand liquefaction of the Christchurch sands. Professor Chibanowski, working with his PhD student Sean Rees, decided to take a typical sand in Christchurch. It was near the Fitzgerald Bridge, so that's why they call it the FBM. And then they decided to mix in the non-plastic quartz silt-sized particles, and they added in 1% fines content, so it's a clean sand, 10% fines content, so it's kind of a SMML, and then 30% fines, so it's an SM, but they're all non-plastic sands, from clean sands to silty sands. Very good testing was done by Sean Rees. He's now actually the director of their geotechnical laboratories at the University of Canterbury. And you can see he established the steady state line for the FBM 30 soil, the steady state line for the FBM 10% fines, and the 1% fines. With that, if I know where I'm at, and let's say I am at this relative density, and I am at this mean effective stress, but I have 10% fines in my sand, I know I may contract a little bit, but I have to get to home. I have to get to the steady state line. It has to go in an increasing effective stress, dilative tendency. Same initial state, but now I have 30% fines. I've got to get to home. Home is the steady state line for the soil with 30% fines. It has to go to the left, which means it has contracted tendencies, and it will develop high excess pore pressures. It will reduce the effective stress. It will be soft. It will be weak. So adding fines increases the compressibility of the soil, and it actually makes the soil have a more contractive tendency in undrained shear. There are people in the U.S., and I've listened to people around the world say, silty sands will not liquefy. Absolutely incorrect. This should let you know, adding a little bit of fines makes the soil want to contract more. Contracting more builds up more positive pore pressure in undrained shear. It actually makes things worse, not better. If I just look at a clean sand versus a sand with only 20% fines, we see, if we establish that steady state line, that because the steady state line is lower, at the same relative density and the same effective stress, the flow regime is bigger. Adding fines makes the soil more compressible, more contractive, all things being equal. Professor Casagrande, when he developed the unified soil classification system, made a big mistake. He said if you've got 50% fines or less, that you are a sand. That's not true. You should have put that dividing line at 25%. Because, as shown by several investigators, if you go from a clean sand, so this is void ratio, and this is the Emax and Emin at every void ratio, at every fines content. So you go from a clean sand all the way to a pure silt, where it's 100% fines. All the fines are non-plastic. That as you start off, you have a sand, and it has voids. As you add fines, the fines fill the voids without affecting the sand structure. Then you get to a point, and Emax and Emin tend to go down because you're filling those voids. But as you get to about 25%, and from some soils it might be 20%, other soils it might be 30%, it may be as high as 35%, but a rule of thumb is around 25%. At 25%, you're getting to the point where when you add fines, you are now separating the grains of sand. Even though it is 40% fines and 60% sand, even though it would be classified as a silty sand, an SM, it's not a silty sand. It's a silt that has sand particles floating in it. And so it acts like silt. And as you increase that, so we don't expect differences in soil responses much when we go from 40%, 50%, 60, 80% fines, because it is a fine-grained soil that has big sand particles floating in the matrix. The matrix is the fines. We expect clean sands to respond a certain way, but as we add a little bit of fines, they basically start to become silty sands, and then they transition over to where they basically become sandy silts. And this, Professor Szymanowski, working with Professor Ishihara, did a very nice job. This is a paper in Soil and Foundations, the Japanese journal in 2002, of taking all these results. One of the things that Professor Szymanowski showed definitively is the American Society of Testing Materials says you cannot calculate or measure an Emax and Emin if you have more than 15% fines. That's not correct. They showed they got reliable, consistent results when they went out to 30% fines, maybe even 40% fines. Use the Japanese method for Emacs, and you should use the Japanese method for EMIN, but the difference between the US and Japanese method for EMIN is almost the same. But Emacs is very sensitive to the method, and the best way of getting Emacs is the Japanese method. It's also the method that Professor Ishihara and Chibanowski used, and they have a lot of good data, so you want to be consistent with them. They did calculate Emacs and EMINs at higher fines content ratios. They'll admit that those are somewhat suspect. And the whole concept of void ratio, Emacs and EMIN really falls away once you have about more than 40% fines. And so maybe when we're talking about silts, we might just talk about void ratio and not Emacs and EMIN. But I still think for these idealized studies, in fact, this is based a lot on work by Lade, knowing this as a framework is useful, because relative density is more powerful than just void ratio. And you can use it up to maybe 30 to 40% fines content. So we wanted to start your morning with something light. You know, soils have a unique steady state line, and we're just going to believe it exists because it makes our life easier. When sheared monotonically, we will get to the steady state if we can keep things homogeneous in their strain response, eventually at large strains. If these two things are true, then knowing the initial state of the soil and the effective stress it's at, and knowing the steady state line, I can predict so many things. I can do so many things that it's worth having this concept. This is the essence of your friend, the state concept, or the critical state framework. Really one of the great inventions of the last century. The state parameter, or the state index, is actually one of the most important things for you to know. In fact, if you could push a cone into the ground and directly, reliably get a good index of the state parameter, that would be more valuable than even relative density. Because that's telling you, given what that soil's void ratio or relative density is, and its confining pressure, and some other things like fines content, where it wants to go. If it basically has a positive state parameter, it's contractive. If it has a negative state parameter, then it is dilative. The fact that they quantify the relative state of the soil to allowing you to predict the shape and the peak of the stress strain curve. It combines this key concept of density and effective confining pressure, so it's really relative density and effective confining pressure. It's reasonably valid across a range of densities and stresses for drained and undrained response, and allows us to understand well-behaved soils. It allows us to understand poorly behaved soils because you have a framework to then deviate from and see things. If you see a soil that is well graded and has highly angular particles, realize it's more than just relative density and effective stress. But you know that if you have a well-graded sand with very angular particles, all things being equal, it would want to be more contractive or dilative in drain shear. Dilative. So now you have a framework that you can move beyond, because it's all about, hey soil, do you want to dilate in drain shear, or do you want to contract in drain shear? And what are those things that make you more dilative or more contractive? I am definitely on the dilative side, because ever since I've come to your country, I've just been eating a lot. And I've been dilating. I should have been eating inside of a pool with an applied stress field, because then I'd be doing work while I'm eating and dilating.